with Proficient, and we'd like to take a few minutes to give you a brief glimpse of one of the innovative and creative solutions we have provided for one of our clients in the cloud computing space. The acronym most appropriately assigned to this project was called Predator. So what is this Predator? Well, it's a dynamic tool that implements automated capacity and workload management functions in cloud environments. Because highly utilized clouds are ever-changing, automation is needed to implement capacity and workload principles across the various levels of virtualization to be most cost-effective. The main business drivers behind the Predator effort were to reduce cloud administration costs via automation. This client will have thousands of virtual machines in their internal cloud. To increase infrastructure utilization. Greater utilization of assets can be done in creative and cost-effective ways with the current virtualization and cloud technologies. End-user self-service can be even more cost-effective if automated services are used to correctly purpose assets. Virtualization sprawl is a common cloud problem, and Predator was designed to prowl the cloud infrastructure and eliminate problems associated with this. Many virtualization technologies do an excellent job of sizing their particular layer of virtualization, but have little input from other layers of the architecture. Predator assists in right-sizing assets because it sees multiple layers of the cloud infrastructure. An extra feature of Predator is that it can track historical and real-time availability of cloud assets. We began our design with the premise that we needed to do three basic things to accomplish the goals outlined in the business drivers. First, we needed to sense the cloud infrastructure in real time, meaning we needed to gather resource and transaction metrics from the assets at all layers of the cloud in a way that would not be technology API or tool specific. This would allow technologies to be added, changed, or removed in the cloud over time and have minimal effect in our capacity and workload management decisions. Second, we needed to evaluate and reason over the gathered metrics and compare them to the capacity of the cloud assets in real time to make logical decisions. We also needed to take into account long-term trending, historical data, and technology and application profiles to shape the reasoning and decisioning. Lastly, we needed to interact with the specific virtualization technologies at all layers of the infrastructure to make changes to best utilize the cloud assets, meet business partner SLAs, and provide the most cost-effective solution. Our solution needed to be elastic in nature and adaptable to an ever-changing cloud environment. We began with a typical virtualized server environment, physical hosts with multiple virtual hosts running on each physical host, and applications or JVMs running in each virtual host. This required resource utilization metrics from all levels on the hosts, plus resource utilization metrics from the virtualization controller. These metrics were aggregated into time-stamped and indexed data stores, where statistical functions could be run against them at given intervals. Transaction metrics, both application and system, were gathered into their time-stamped and indexed data stores for statistical analysis at given intervals. A cloud allocation database was built to maintain application-specific information such as SLAs, cluster minimum and maximums, resource pool information, application group information, and much more. At the heart of the system was a business rules engine residing within a framework that provided I/O and interfacing to the cloud. An external rules repository was implemented so that the rules would be dynamically pulled by the engine and could also be maintained outside of the engine. This also allowed non-Java programmers to manage the cloud infrastructure rules. At a given interval, the business rules engine would be fed information by the framework from the cloud allocation database, transaction metrics, and resource metrics, and create facts within the engine. The engine would pull the rules from the external repository and fire them over the given facts. The outcome of the REAT algorithm were derived facts that the framework would listen for. These derived facts were recommended changes that would accomplish the goals of the business drivers. CEP, complex event processing, was used to provide windows for control of time scope decisioning. The recommended changes would then be transformed to commands that would be executed by the appropriate technology. After the changes had been made, the cloud allocation database would be updated to reflect the current state of the cloud. If you have questions about this cloud solution or would like to contact us, you may do so at sales@perficient.com. You can also follow us on Facebook or Twitter.